Okay, I still don't see Dr. Thomas. I cannot see the audience, so I don't know how many people are there right now. But I guess we're gonna start in a few seconds. Oh, Dr. Thomas, you're on mute. Okay, Dr. Thomas, according to the webinar, you're the first one. Do you still want to be the first one?
Oh, okay. Yes, I can be. Sorry, I thought that I was last according to the program, but I can speak first if necessary.
Okay, are you ready to? Let me see. Let me give you. Okay, so Dr. Thomas, you're going to be the first one, right? Hello, can you hear me?
Yeah, I can hear you.
Okay, you will be the first one, right?
Mm-hmm.
Okay, let me start. Hi, everybody. This is the session B, characterizing traffic-related air pollutant. Today we have 4 speakers. Each speaker will speak for about 15 minutes, and we would have about a couple of minutes for quick questions. And after everybody spoke, we would have about 5 to 10 minutes for the audience to ask a question to any speakers. Okay, so that's the game plan. Today, the first speaker is Dr. Daisy Thomas. Dr. Thomas works for 3Dex Corporation, and she is their lead automotive research engineer. Dr. Thomas has over 5 years experience in automotive emission research with a PhD in engineering that focused on real-world emissions from hybrid vehicles and the impact of biofuels from her PhD is from the University of Leeds, UK. Dr. Thomas, it's all yours.
Hi, thank you for the kind introduction. And good afternoon to everyone in the US or on that side of the Atlantic, and good evening to everyone further east, like myself in the UK. Today I'm going to be presenting some results looking into the effect of the COVID-19 pandemic lockdown in the UK and the effect that this had on the air pollution levels specific to London, using the case study of a single London street to investigate this. So I'm going to start by introducing the UK coronavirus pandemic situation in the UK and the lockdowns that were enacted as a result of this. I'll then go on to look at how this affected the transport use in the UK, and then look specifically at the ambient levels of NOx and PM or particulate matter in the air in London, studying a specific London street. So in March 2020, the UK entered its first COVID-19 lockdown, and this led to a sudden reduction in road traffic. And so we thought it was a very good time to ask the question, what is the impact of reduced traffic on air quality? And so in order to try and start to answer this question, today I'll be presenting a study into the air quality at a particular central London road called Marylebone Road, which is one of the busiest roads in London. And there's an air quality monitoring site located on that road, which I've been using the data for to have a look at how the air quality has changed through time and compare this back with national traffic usage data which tells me how the levels of vehicles changed during the pandemic and the lockdown specifically. So this first figure here shows the relative percentage of the road vehicles during the year of 2020 when the pandemic hit. And so this is using the first week of February 2020 as a sort of baseline. And then, so that's 100% on this scale. And then we see indicated on the figure where the UK lockdown occurred. And so we can see that the levels of traffic drastically reduced when the UK was put into lockdown. But by looking at the legend on the right-hand side, you can see that the cars in green reduced a lot more than the heavy-duty vehicles, which are indicated in red. So the levels of cars were only about 30% of what they were before lockdown when they reduced to their minimum, whereas heavy-duty vehicles only reduced to about 60% of their pre-pandemic levels. And another thing to notice is that although the levels quite quickly reduce, they immediately start coming back up again. So people didn't sort of carry on abiding by the lockdown rules so specifically maybe, or there was just a need for extra transport during that time. But you can't, if you look at the end of the lockdown period, the levels of car usage and heavy goods usage is actually quite similar to what it was before the pandemic hit and before the UK was put into a lockdown. So first of all, I'm going to have a look at the effect that this had on the NOx pollutant emissions. So here we have some bivariate polar plots, which basically are quite a useful way of representing ambient concentrations of pollutants in the air, because when you have an air quality monitoring site, they're quite affected by the wind speed and direction in that location. And so you need to account for this when you look at the pollution quantities, and when you're comparing between years for a particular site, you need to account for the fact that the wind speed and direction may be different. So looking at 2020 in the bottom right hand of the figure, we can see that the color is more blue, which is associated with a much lower concentration of NOx compared to the previous years, which are seeing more yellows and reds, which, as you can see on the scale, is associated with higher levels of ambient NOx in the air. So we can see that between the dates of the 23rd of March and the 27th of April here in 2020, that there's a lot less pollution than for this same time period in 2019, 2018 and 2017 respectively. So the lockdown does seem to be reducing the levels of NOx in the air. Now to look at the concentrations of NO and NO2 individually. So these figures on the right-hand side show the transient air quality levels at the Marylebone site in black for NO on the top graph and NO2 on the bottom half graph. And then in blue, we have the cumulative levels, just to more clearly be able to see the effect that this is having on the total levels that are around during the time. And the lockdown is delineated by this red line here. So we can see quite clearly that the levels of both NO and NO2 are decreasing quite drastically when the UK is put into this lockdown. But what you will also notice is that the levels of NO are decreasing a lot more than they are for NO2. And when we look at this amount of decrease for NO, we see that it's about an 88% decrease, whereas for NO2, it's only a 62% decrease. So we're definitely seeing more of a change in the NO than the NO2. And we think that this is caused by the fact that the light duty vehicles were reduced in the amount of traffic that there was being seen more than the heavy duty vehicles. And so because in the UK, light duty vehicles are about 50-50 gasoline and diesel, we would see more of a reduction of NO compared to the heavy-duty vehicles producing predominantly the NO2. And now to look at PM10. So again, presenting these bivariate polar plots, we can see some decrease that has resulted when we think of the colours that we see being more blue for this 2020 year compared to the previous 3 years. But it's not as drastic a result as we saw for the NO2 and NO previously. When we calculate how much this actually is, it's a 20% decrease when considering PM10 or a 26% decrease when considering PM2.5. So we're seeing not quite the same level of decrease as we had seen for the NOx previously. And when we look at the year 2020 on itself, we can see actually that there's very little change compared to the pre-lockdown for this year. And so this indicates that perhaps the differences that we're seeing for this 23rd of March to 27th of April timeframe may be caused by other external factors that aren't particularly to do with the lockdown itself necessarily. As Chair Randolph mentioned in her keynote speech, there are many different sources of air pollution. And so just reducing the traffic may not be having so much of an effect on PM10 in this case, or PM2.5. So this presentation has shown how the lockdown has affected the motor traffic usage in the UK, and then looked at how this affects the amount of air pollution in a busy urban centre, using a particular London street as an example here. So we saw that the road traffic decreased during the lockdown, but a lot more for light duty vehicles than heavy duty. So we saw about a 30% level of cars on the road compared to the pre-lockdown levels, but about a 60% level of heavy-duty vehicles, so not as much of a decrease. And as a result, we saw that NO reduced a lot more than NO2 did during the first month of the lockdown when compared to previous years. So that was about 88% decrease for NO and a 62% decrease for NO2. Meanwhile, PM did not decrease as much as we would expect based on the NOx values. So we just saw a 20% decrease for PM10 and a 26% decrease for PM2.5. But as I discussed previously, this may actually not be so closely related to the lockdown as the NOx reduction that we saw was. So these results show the potential for drastic action to improve our urban air quality. But it's also demonstrated quite starkly that it's not such a simple problem to solve, and a very targeted approach is needed. So, for example, to think about the electrification of the light-duty vehicle fleet, it must be considered that this might not have quite the same impact on the pollutants that we consider to be most dangerous for human health as one would perhaps hope. And we need to make sure that we think very carefully about how we reduce the levels of pollution in our urban centres. And also, I just wanted to note that it should be remembered that the pollutant concentrations that I've discussed today are only representing a single air quality monitoring site, so aren't wholly representative of the levels of pollution in London or in the UK in total. And then I just wanted to end on some final thoughts regarding the fact that many researchers around the world are linking increased levels of air pollution with increased COVID-19 mortality. So many of the diseases such as asthma that are known to be associated with increased air pollution also increase the risk of mortality from COVID-19. So these populations that are already being put at risk by being in close proximity to vehicles and the air pollution that they produce are now being even more disproportionately put at risk from COVID-19. And secondly, particulate matter pollution may also be a vector itself for the spreading of COVID-19 by providing a surface onto which the virus can stay suspended in the air for longer periods of time and also allow it to be transported deeper into the lungs. So there's now even more reasons to improve our air quality compared to before the times of COVID. Thank you for listening.
Thank you, Dr. Thomas. I guess we can take a couple of questions if there are any questions from the audience. Okay, I have not seen one, but I do have a question for you, Dr. Thomas. I noticed that you mentioned the PM10 and PM2.5 did not show any decrease during the COVID-19 situation. Do you know why is that?
Well, I think that it would just be that other factors are affecting the PM concentrations more than the traffic. So although the traffic is reducing, there's a whole host of other sources of particulate pollution that may be overriding the impacts that we see from the traffic reduction.
I see. Okay. Let me see if there are any. Okay, here I have a couple questions. Let me take one more. Why are NOx levels much less in 2019 than 2017 and 2018?
So this is a good question. Like the NOx levels, when you look year on year, you are seeing a general decrease in the levels of NOx year on year due to more stringent legislation limiting the types of vehicles that are allowed into London city centre. But when you look at them with the year 2020 as well, you can see a much more drastic reduction, and this is only over the period during the lockdown. So you can infer that it's caused by the lockdown.
Okay, I guess we have time for one last question. This is a question from the audience. The question is there a reason why nitric oxide decreased more than nitrogen dioxide? And also, did you look into the vehicle fleet composition in terms of electric vehicles, hybrid, or IC EV?
Yes, so the data that I used did have in the light duty vehicles, it did actually have electric vehicles listed separately. So these are all internal combustion engines. But I think that if I remember correctly, I think that it's both hybrids and non-hybrids involved in it. In terms of the wider fleet composition, as I mentioned in the first part of the presentation, there were the reduction of the heavy goods vehicles was not as pronounced as the reduction in the light duty and personal vehicles, which was the reason for the difference in the NO and the NO2 levels, because in the UK, about 50% of the light duty cars are diesel and 50% are gasoline, whereas for heavy duty, obviously majority diesel. So most of the NO2 was still being produced from these vehicles.
Okay, thank you, Dr. Thomas. Let me move into our next speaker. Our next speaker is Dr. Tom Gill. Tom is a professor of Earth, Environmental and Resource Sciences, Environmental Science and Engineering at UTEP. That's a very long title. He has a PhD in Earth Science and Resources and a BS in Atmospheric Science from UC Davis. He is a registered geologist in the state of Texas and a fellow of the Royal Geographical Society. Prior to joining UTEP, he worked as a research faculty member at Texas Tech, a physical scientist for the USDA, and a postgraduate researcher at the Crocker Nuclear Laboratory of UC Davis. He has more than 30 years of research experience in understanding atmospheric particulate matter, particularly dust, with a focus on understanding its sources, composition, and its impacts on humans and the environment. So with that, Tom, please start.
Okay, Thank you, Wen-Whai, and good day, everybody. I am going to present our research regarding dust and particulate matter affecting Interstate 10 at Lordsburg Playa in southwestern New Mexico, United States. And Lordsburg Playa is about midway between El Paso, Texas, and Tucson, Arizona. For those of you not familiar with the term, a playa is a geographic or geological term for a dried up lake bed. Playas are Earth's most intense source areas of dust storms and arguably most intense source areas of soil-related particulate matter. Lordsburg Playa, which is in the Chihuahuan Desert of New Mexico, is no exception. Dust emissions from the surface of Lordsburg Playa have been causing major risks to public health and the environment, and especially to traffic safety on Interstate 10, which directly crosses the surface of the playa. So the dry lake bed is bisected by this major interstate freeway. And that creates a major problem, a major particulate matter safety hazard. According to the World Health Organization, before the pandemic, traffic crashes on roadways were the 9th leading cause of death worldwide. And it is no different in the United States. Here on Lordsburg Playa on Interstate 10, more than 15,000 vehicles per day cross the playa, and approximately 30% of them are heavy-duty vehicles, especially trucks, because this is a major transportation corridor for goods across the United States. And just imagine going down the roadway at 70 miles an hour and suddenly running into a blinding cloud of dust like this, where suddenly the visibility goes to zero. And it has become a major safety and health hazard through this sudden extreme particulate matter clouds from the playa that drivers experience. In fact, some new research we've completed confirms that Lordsburg Playa on I-10 is the single most hazardous stretch of road in the United States for dust-related highway crashes, with at least 41 fatalities in recent decades, and maybe as much as 50% more than that, depending on how the records are classified. And even though the state of New Mexico has both fixed warning signs emphasizing the dust hazard and dynamic warning signs over the freeway that can flash warnings when dust conditions are anticipated, we still have horrible crashes like this that have taken dozens of lives. So this was the motivation of our project, to try to assess some of the issues that are leading to the hazard, to assist in efforts to mitigate it. The first step was to look through catalogs of satellite imagery of Lordsburg Playa from multiple platforms, as well as other data sources, including soil maps, to try and determine which parts of the playa are recurrent dust source areas, basically the areas where the greatest hazard of dust emission exists that may need to be mitigated or understood to understand the risk to traffic. Guided by that, we began field sampling and surface erodibility and dust emissivity testing on the playa itself, both near the roadway, as you see here, as well as very far from the roadway along the edges of the playa. This is on the north side of the playa, and this kind of almost mirage-looking line in the distance is roughly where the interstate highway crosses. Soil sampling and analysis of the soil, as well as measurement of the surface soil properties, both in situ and in the laboratory, showed why, to some extent, this is a problem. The surface soil in the erodible parts of the playa was found to have an extremely high inherent PM10 content in the soil itself. It's incredibly fine, incredibly dusty soil. If you break the surface of the soil, it's almost an unlimited reservoir of PM10, where as much as half of the soil particles themselves are in the PM10 size mode. We also looked at the composition, the chemical and mineral composition of the soil itself. Since this is a historic mining area for lead, zinc, antimony, and other metals, there is some concern about ore minerals and metal-bearing minerals having very high concentrations on the playa. Fortunately, we did not see the minerals themselves being characterized by metal ores, although as we will see later, there was some runoff of metal-bearing deposits into these sediments that could then add an additional risk just from the PM itself, from metals or other potentially hazardous components in the particulate matter. We deployed portable instrumentation on the playa to measure particulate matter emissivity, particularly this device called a pie swirl. A pie swirl is a miniature wind tunnel that is very portable and can be used to test the wind erodibility and particulate matter emissivity of different natural surfaces. And so we tested the PM10 emissivity and dust erodibility of different surfaces of the playa with this device. We have a paper already published by Van Pelt et al., Geoenvironmental Disasters 2020, that gives comprehensive data on this PM10 emissions and erodibility of the playa. We also measured the potential bioavailability of metals in these dust emissive surface soils that could lead to additional exposures to heavy metals to motorists and public safety personnel caught in dusty conditions at the playa. We did that by leaching the dust, the fine fraction, the PM10 fraction of dust emissive sediments in simulated lung fluids for different amounts of time. Then we did modeling. First, we used a model called SWEEP, which stands for the Single Event Wind Erosion Evaluation Program, which is a model produced by the U.S. Department of Agriculture to measure dust and particulate matter emissions from agriculture and rangelands. We worked with USDA personnel to adapt that model to bare or sparsely vegetated playa surfaces, and adapted that model to several particular areas on the playa, both near and far from the highway, that were identified as dust hotspots. The SWEEP model provided PM10 emission outputs at the source areas, but then to basically take that PM10 and transport it to the receptor site, which is the highway, we coupled those SWEEP outputs as inputs to the US EPA's AirMod model. AirMod is a very widely used dispersion model for particulate matter dispersion. So we coupled the SWEEP outputs to AirMod to have AirMod then transport that particulate matter from the playa dust sources to the receptor site, which is the Interstate 10 highway. And from that, we could estimate short-term particulate matter exposures in dust on I-10 from dust that was raised from the hotspots on the dry lake bed. Our findings were that the threshold friction velocity, which is a measurement of the wind needed for dust emission, was very low along the deltas and shorelines, meaning that the deltas and shorelines and basically edges of the lake bed had a very low threshold for dust emission compared to the center of the lake bed, which is relatively stable and is sometimes flooded. We found PM10 fluxes up to 50 times higher in disturbed areas, delta areas, and the edges than in the interior part of the lake bed. The consolidated surface at the center of the playa would require winds exceeding 50 miles an hour at a minimum and likely much higher to pose national ambient air quality standard exceedances. But the shorelines and the disturbed areas were up to 30 times more likely to produce at least short-term exceedances of national ambient air quality standards than the natural undisturbed playa. Lead levels and bioavailability and copper levels and bioavailability were highest near the roadway, probably an artifact of traffic-derived heavy metal pollution deposited on the soils near the edge of the highway. Copper was also higher in the far lakeshore, and zinc was well distributed throughout the areas we sampled on the playa, probably reflecting not only traffic-derived pollution, but natural minerals and mining waste. And while notable, the risk to motorists and highway workers from these metals is probably low, given the fact that even though the PM10 concentrations are extremely high, the exposures are brief. And by PM10 concentrations being high, the sweep and AirMod results suggest that near highway short-term PM10 concentrations were modeled to exceed 100,000 micrograms per cubic meter. Now, that may seem amazing to people, to you who are familiar with PM10 concentrations in the environment, but these are actually, remember, very short term, but they're consistent with modeled and even measured concentrations of PM10 dust at other playas, illustrating how thick and dense these PM10 clouds are when they sweep across the highway. These data have provided support to stakeholders, agencies such as the State of New Mexico Transportation and Environment Departments, trying to make efforts at mitigation of the dust hazard on the highway, and can be used to help try to understand and increase mitigation of this risk, which led through U.S. Department of Transportation funding to the state of New Mexico, is really providing great results. The project has provided a great educational opportunity to several students, including Iyasu Ibadingal on the left, who received his PhD degree last weekend, Julieta Saucedo on the right, who did the lab work for the metals, who received her bachelor's degree last weekend, and also Marcos Mendez, who is a MS student in candidacy for the MS at UTEP. I'd like to thank the many stakeholders and partners who we work with, including co-PI Lashinjian at UTEP, Scott Van Pelt and John Tartarko of the USDA, John-Ron Lee of University of Tulsa, the USGS, who provided some of the analysis, and the stakeholders and partners with the state of New Mexico. And thank you to CAR-T and also Leverage support from NASA for support to this project.
Thank you, Tom. I guess we have time for probably just one question. Let me see if there's any question from the audience. Okay. Well, let me ask you a quick question, Tom. When you run your sweep in AirMod, did you use the time varying emission? That would be emission by hour, or you're using just a worst case emission?
We actually did, I believe, both, but we generally tried to assume, the worst case scenario to try to understand the maximum levels of PM10 that would be found in those dust clouds along the highway. There were some limitations with the way that AirMod is set up and worked to try to understand very, very short-term exposures. So we tried to go with the worst case scenario, I guess you could say, for the extreme emissions.
Okay, thank you, Tom. Let's move to the next speaker. I guess, Dr. Kim, you upload your file while I'm introducing you. Dr. Daejin Kim is an assistant professor at Gangneung-Wonju National University in South Korea. His research interest includes various fields of transportation, energy, and air quality. He received a PhD degree in transportation engineering from Georgia Tech. He's an expert in developing advanced modeling tools for traffic-related pollutant dispersion modeling. With that, Dr. Kim, it's all yours.
Sure. Thank you for inviting me. Can you hear me? Can you see my screen?
Yes.
Okay, let me start. Okay, good afternoon, everyone, and thank everyone for coming to listen to our research. My name is, again, Daejin Kim, and I am currently an assistant professor at Gangneung-Wonju National University in South Korea. So actually, today I am joining from South Korea. So today I will present our research called Dynamic Grid Receptor Method for Regional Level Near-Load Air Quality Analysis, a case study for particulate matter. So this study was actually conducted as a part of my doctorate dissertation research, titled Large-Scale Dynamic Microscopic Simulations for Region-Wide Line Source Dispersion Modeling, which was conducted at Georgia Institute of Technology. So in terms of the background of this research, the literature review indicates that with increasing concerns on the human exposure to traffic-related air pollutants, a number of modeling tools have been developed to predict the traffic-related pollutants concentrations at regional or sub-regional scales. So for example, some research incorporated MOVES and air mode for the transportation conformity analysis at the regional scale. But because of the computational issues on dispersion modeling at regional scale, most previous models have applied uniform grid receptors at relatively low spatial resolution, which is very useful for exploring the overall spatial distributions of pollutants concentrations. However, these approaches have been limited in that the predicted concentrations are necessarily biased because receptor concentrations are very sensitive to the distance between receptor and pollutants link sources in a nonlinear manner. So in terms of the simulation time for dispersion modeling, the pilot study that was conducted in this study indicates that the air mode simulation time increases with the number of links considered, showing that the total air mode runtime for the Metro Atlanta roadway network case for a single receptor could take about around 11 hours on average with a single desktop computer. So, and in addition, the air mode simulation time also increases with the number of receptors considered, showing that the total air mode runtime for processing around 10,000 receptors for single link source could take around 2.5 hours on average. So these results suggest that the dispersion modeling time increases significantly with the link receptor combinations. And for the Metro Atlanta network case, the air mode runtime to process a dense receptor layout could take over an year on a general single desktop computer. So these results suggest that regional scale dispersion modeling requires more efficient modeling framework. So the primary goal of this dissertation research is to develop the comprehensive modeling framework, which is user-friendly, that minimizes the data input preparation and manual labor through streamlined and integrated emissions and dispersion modeling processes. And in addition, the developed modeling system is designed to improve the computational efficiency of the dispersion modeling that could reduce the model bias and provide reasonable model runtimes. So this is the main contents of my dissertation research, and there are actually three main research topics, including the dynamic grid research model and supervised link screening model and high performance computing. That aims to improve the dispersion modeling predictions and efficiency. Especially today, I'm going to describe the development of the dynamic grid receptor model. And by the way, for more information about my dissertation research, please refer to the reference attached to the bottom. So the literature review indicates that the proper receptor distribution is crucial for producing unbiased concentration estimate, especially because the traffic-related pollutions demonstrate steep gradients in concentrations within the near road areas. And the great variation can lead to uncertainty in evaluating the near road concentrations and resultant human exposures. However, most of the previous studies have used relatively low resolution gridded receptor settings, such as 200 meters by 200 meter receptors, potentially because of its simple implementation as well as to reduce the total model run times. However, because increasing the number of receptors to reduce the model bias can result in a longer total processing time, an optimal receptor setting is needed to predict the desired concentration profiles while minimizing the total computation time. So to overcome the challenges addressed in the previous research, this study developed a strategic receptor placement method, which is called dynamic grid receptor models. And to develop the model, we ran the numerous R-line simulations to generate enough training and testing data set. And the outline simulations were conducted with a hypothetical network of a total of 1,200 meters, which is composed of 3 transportation links as shown in the figures to the bottom. And the high density receptor grid was set at 5 meters by 5 meter resolution to predict the pollutants concentrations at the high density receptor sites. And here for demonstration, this study ran the simulations for PM 2.5 concentrations. Then it conducted 1,000 R-line simulations, simulation runs for generating training data set, and 300 runs for the testing data set. And for each simulation, it generated uniform random input parameters, and the ranges of the input parameters were set based on some references as shown in this slide. And the figures in this slide show some examples of the PM2.5 concentration profiles as predicted by the outline simulations. And as shown in this slide, the spatial distributions of the PM2.5 concentrations vary depending on the input parameters such as wind speed, wind direction, and link emissions, etc. And all these figures may suggest that the concentration profiles vary significantly by the simulation parameters, and this may suggest that a sort of strategies for proper receptor locations is needed to better capture the near-root concentration profiles. So as a way to determine the optimal locations of receptors, this study applied a stepwise receptor search method. The process iteratively finds the best receptors that better approximate the concentration profiles as predicted by the high-density receptor settings. And for each training sample, the model sets a total of 121 candidate receptor sites as shown in the figure to the left bottom. Then it begins with the 4 reference receptor sites that are located at the corners of the receptor's area. And through the forward search, it iteratively finds the receptors that best fit the PM2.5 concentration profile until the marginal changes in the mean square error is less than the preset threshold of 0.001 micrograms per cubic meters. Then after the forward search processes, the backward search removes the receptors that worst fit the PM2.5 concentration profile until the marginal changes remain within the threshold. And as such, this study identified the optimal receptor locations for the 1,000 training samples, and the result showed that around 6 to 23 receptors were selected through the processes with an average of around 13 receptors. And the results suggest that with only a few number of receptors, the optimal receptor placement can approximate the concentration profiles as predicted by the high-density receptor settings. As such, the optimal receptor locations can be identified by approximating the concentration profiles as predicted by the high-density receptor setting through the stepwise processes. However, the concentration profiles at such high-resolution receptor setting are practically unknown. So this study proposed to develop the dynamic grid receptor model based on the optimal receptor locations, which was identified by the stepwise processes and some of the influential outline variables which were used for the outline simulations. And the proposed dynamic grid receptor model consists of 2 main models. The first model is to determine the optimal number of receptors, and the second model is to determine the optimal locations of receptors given the optimal number of receptors. And especially, the first model was developed based on linear regression, as shown in this table, where the dependent variable is the optimal number of receptors, and a set of explanatory variables were tested initially, and finally, after excluding some of the insignificant variables, the absolute difference in link emissions with respect to the adjacent link segment and wind speed, wind direction were found to be significant variables in determining the optimal number of receptors. Then for the second model, a total of 121 logistic regression models were developed for each candidate receptor site, where the dependent variable is a binary case where whether or not the the receptor site is chosen for the optimal receptor location. And the same set of explanatory variables, which was used for the first model, as well as the optimal number of receptors, were used as the explanatory variables for the logistic regression models. And to summarize, the dynamic grid receptor model first determines the optimal number of receptors. Then the second model estimates the probabilities of being chosen for the optimal receptor locations for each candidate receptor site, as shown in the figures to the bottom. And finally, the model selects the receptor sites of the highest probabilities given the optimal number of receptors. Then to test the dynamic grid receptor model, this study applied the dynamic grid receptor model to the 3 case study areas in the city of Atlanta, as shown in this slide. And for each study area, the annual average PM2.5 concentration profiles were predicted by using the air mode. And this slide shows the receptor placement for the city of Decatur, which were generated by the dynamic grid receptor model, as well as the static grid receptor placement receptor model for comparison. And the figure to the left shows the receptor placement by the dynamic grid receptor model, suggesting that the model tends to place. Excuse me? Okay. Dense receptor, suggesting that the model tends to place dense receptors in near road areas. And for comparison, the static grid receptor model sets the receptor site with a similar number of receptors as the dynamic grid receptor models, which is about 70-meter receptor resolution, as shown in the figure to the right. And this slide shows the annual average PM2.5.
1 minute.
Hello?
1 minute.
Okay. Okay, so this is the result. And this slide shows the annual average PM2.5 concentration profiles generated by both of the models. And it shows that overall the dynamic and static grid models produces somewhat similar concentration profiles as shown in this figure. However, the figure in this slide shows that the dynamic grid model tends to predict higher PM2.5 concentrations for the near road areas than the static grid models, suggesting that the dynamic grid model may be better for identifying hotspots. Okay. Okay, to summarize, this study is meaningful in that it identified the fundamental relationship among dispersion model input parameters and predicted near-road pollutants concentration profile. And for example, it shows that the concentration profiles vary by various parameters such as link emissions, wind speed, and wind direction. And as such, it can help identify the preferred locations of receptors that can produce unbiased concentration profiles, and the results show that the strategic receptor placement method developed in the study only requires a few number of receptors that approximate the PM2.5 concentration profiles as predicted by the high-density receptor models.
Okay, thank you, Dr. Kim. I guess we probably need to defer the questions to you till the end of the session. Okay, let's move to our next speaker, Amit, who is an assistant professor in the Department of Earth, Environmental, and Marine Sciences at the University of Texas, Rio Grande Valley. He received his MPH and PhD from the University of Texas, El Paso, and MS from Carnegie Mellon University. He is an expert in air quality and public health. Amit, it's all yours.
Hello, good afternoon, everyone. I don't know why my slides. Okay, here we go. Okay, good afternoon, everyone. Thank you, Dr. Lee, for that kind introduction. So, the title of my presentation is basically Elemental Analysis of PM 2.5 at 4 schools in El Paso, Texas, and Ciudad, Juarez, Chihuahua, Mexico. And this work was part of my doctoral research, which I did under the tutelage of Dr. Lee at UTEP. So at the beginning, I would like to mention that this study was done in 2008, but the elemental analysis was just done recently. So in the beginning, I will explain like some of the initial findings, and then I will be focusing more on the elemental part. So as you can see, this is a Google Earth image of the Paso del Norte region, which is basically two countries, United States and Mexico. And then you have 3 states, Texas in United States, and then the state of New Mexico, and the state of Chihuahua in Mexico. And today our area of focus is basically El Paso, Texas, and Ciudad Juarez, Chihuahua. This region has experienced rapid population growth. We have had, this region has also experiences heavy traffic air pollution. We have a couple of international port of entries between United States and Mexico. In fact, the Bridge of Americas that we have here in El Paso is the second busiest port of entry on the US-Mexico border region. In addition, this area is at a higher elevation, about 4,000 feet above the sea level. So it's arid weather, and then we have frequent winter stagnations as well. So the genesis of the study was we wanted to understand the impact of traffic air pollution, certain pollutants, and the respiratory health effects in school-going asthmatic children. Because we thought that central ambient monitoring sites are not an accurate representation of the actual exposure of school-going children at the neighborhood level. We all know that children spend about 8 waking hours of their time, of their daily day at school. So understanding their exposure at school is very important. So this is something very important about our study. This was a study funded by PAHO, Pan American Health Organization. It was the first binational air pollution study conducted in this region. The sampling for particulate matter, we also assessed nitrogen dioxide, black carbon, etc., and other air pollutants, but I'll be just focusing on PM 2.5 today. The sampling was done for 16 weeks at 4 schools. It was a concurrent sampling. So we had schools in low traffic zones and high traffic zones. The low traffic zone school in El Paso was designated as EPA, and high traffic zone was EPB. EP stands for El Paso, of course, and then Ciudad Juarez low traffic was CJA, and then high traffic was CJB. These are some Google Earth images from my doctoral thesis. As you can see, the EPA is the elementary school in the low exposure zone. Was basically in a residential area, and on the left you can see the topography that you see are the Franklin Mountains. The school in the high exposure zone in El Paso was right on the US-Mexico border. The yellow line that you see is basically the US-Mexico border. And then adjoining this border, we have this border highway, which is the major road, and that experiences a lot of traffic as well. This is the school in Ciudad, Juarez. You can see that it is also in a residential neighborhood, but towards the left-hand side of the school, you can see that there is a playground devoid of any vegetation. And so whenever we had dust storms in this region, the concentrations for PM 2.5 for the school were very high. And then this is the school in the CJB, the school CJB in the high exposure zone for Ciudad Juarez. You can see that the school was crisscrossed by these two major arterial highways. Towards the north, we also see a bus terminal where you can see all those yellow buses. So the concentrations for most of the pollutants were also very high at this location. We used the Harvard cascade impactors for this study. The flow rate was about 5 liters per minute, and the PM 2.5 mass was collected on Teflon filters. We did 48 hour sampling twice a week, that is Monday to Wednesday. The filters, the cascade impactors were deployed on Monday, they were retrieved on Wednesday. And then again, after the impactors were retrieved, we installed new set of impactors to assess the exposure from Wednesday to Friday. So we had 48 hours sampling twice a week. So 48 plus 20, 48, that's equal to 96 hours. So that, this strategy was done so that we could get enough data for epidemiological analysis, which was done by folks at Emory University. The mass concentration and the gravimetric analysis was, of course, performed at UTEP. And then finally, after we did this elemental analysis here at UTRGV, University of Texas, Rio Grande Valley, where currently I'm a professor, assistant professor. And this was just done a few weeks ago in the Department of Chemistry. Now, this is the setting of the cascade impactors. This figure is from the library and one of the computer rooms. These are some box plots for PM 2.5. I'll be just focusing on PM 2.5. And as you can see, the concentration levels in Ciudad Juarez were almost twice that of the El Paso schools. And also the school in the high traffic zone in El Paso had much higher measurements than the low traffic school. So the important findings of our study based on the gravimetric analysis was that substantial spatial variability in PM concentration was observed. And CAMs, which are the central ambient monitoring sites, are not an accurate representation. And this study was also unique because not only was it a first binational study done concurrently, but we also did the indoor and the outdoor exposures. The measurements were done both inside the school as well as outside the schools. Outside the schools, most of the samplers were basically on the terrace of the schools. Now, this is, everyone is pretty much aware about elemental analysis, the process. So the samples were digested, and then after the digestion process, they were analyzed by this EPA method 2009, which was like determination of metals and trace metals in water and waste by inductively coupled plasma atomic emission spectrometry. And then the instrument was calibrated using linear calibration curves, etc. And the Department of Chemistry folks found out that the correlation coefficients were pretty cool. R square was like about 0.998. Now these are this is like the analysis is still in progress. These are just some of the basic findings and measurements that I have incorporated on this slide. So PM 2.5 from the gravimetric analysis is in micrograms per meter cube. And then some of the elements that we focused on, and actually I cannot see that because my cam is kind of blocking the the slide, but that's okay. So preliminary analysis suggests that geogenic elements like sodium and potassium, these are the ones that are a little bit high, but we are talking about nanograms per meter cube. And then some of the other elements that we looked at was iron, copper, and then zinc, etc. Um, I have tabulated the results as per the schools and the indoor and the outdoor environment. And surprisingly, the indoor concentrations for sodium in nanograms per meter cube for the school at EPA and EPB were a little bit higher than the outdoor ones. And similarly is also the case for the Ciudad Juarez schools. So this is something that I would be investigating further on. Uh, and then I anticipate that I still need to do the correlation analysis and so many other like principal component analysis and enrichment factor analysis because we'll be working on a manuscript pretty soon based on this elemental analysis data. But I understand that El Paso and Ciudad Juarez being in an arid area, like the geogenic elements, their concentrations would be much more higher than the anthropogenic, than the elements which might have some anthropogenic sources. Resuspended dust, soil erosion, vehicular emissions like tailpipe, brake and tire wear, engine abrasion can be some of the sources. Okay, that finishes my presentation. I'll be happy to answer any questions that you may have.
The forum is open for any questions to any. Let's start with Amit. Are there any questions for Dr. Raysoni? Okay, let me see. If not, I do have a question for Dr. Kim. Since I'm the moderator, I have the privilege to ask questions first. Dr. Kim, this is a very interesting presentation. I think you're pushing the limit of the Gaussian model. My understanding is you have more than 100,000 link for the sources within a small domain about 1 kilometer by 1 kilometer. Is that correct?
Actually, this model was to the models the whole Atlanta areas. So my dissertation work is to model for the whole metro Atlanta areas. But in this particular chapter, I only applied the dynamic grid the models for the small areas, the case study areas. So which has around 1,000 links in the analysis.
Okay, and within a domain of 1 kilometer by 1 kilometer.
Yes.
For your large study for the whole city, since you have so many road links, how do you distinguish the wind speed and wind direction for different links? Did you use multiple weather station data, or you use only one station of meteorological data?
Actually, okay. So for the modeling, I just use the the Georgia EPDs, the AirMet data provided by EPD, so which has the 3 years of meteorology data for the Fulton County areas. So which was, I think, based on the station data from the airport from the Atlanta areas. as I understand.
Surface station and upper air station data. And I guess my question is, for so many links of sources, you have over 100,000 links, but you're only considering one wind direction and one wind speed at any given hour. Are you kind of stretching the limit, because you really cannot see the resolution or how you design for your so refined source grid, but you have only one wind direction and one wind speed? And also, by doing that, I guess you're encountering, you're pushing a Gaussian model's limit. Your receptors are very close to your road links and maybe sitting on inside the road, the source. And have you considered any uncertainty analysis for that?
Yes, but I couldn't do that for my dissertation work. But yeah, I accept that there are some limitations of my dissertation work. So as you mentioned, I only use the media range data for one single station data. So for the next work is to the further consideration consider the media radar for different areas. And also for your second question, um, but actually, this work is to identify the hotspots. So the hotspot, the for the traffic-related emissions, is it should be the near road areas. But the previous work did not consider the high pollutants concentration near road areas. So I think at least my work is provide some better the modeling works for to identify the hotspot in near road areas. Dr. Lee, you are muted.
Thank you. I will ask you another question from the audience. The question is, do you have a paper out which we can read? If there is one, can you send the link or your dissertation to us? Is it published, or is your dissertation in open access area?
Yes, two of my papers for the other chapters are published, so I can share my papers here. But for this work has not been published yet. It's under review. So yeah, maybe. Yeah.
To the audience through the public chat. Let me ask another question from the audience, since we have a little more time. Oh, where did it go? I thought I saw a question for Dr. Kim, but no? Okay. All right. Any other questions from the audience for any of the speaker? Okay. Let me see. No. Okay. Dr. Kim just sent two links through the public chat. So if you're interested, go ahead and download it, or just save the link so you can get the reference later on. Okay, if there's no more question, this concludes our session, and I thank everybody for attending this session, and I thank every speaker for a wonderful talk. So let's all give you a big applause. Okay. 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 All right. Bye now. We'll see you guys in different session.